Okay, at the end of video 5, we were covering 1,2, and 1,4 product addition. So here we have another example of how 1,2 and 1,4 addition are possible with conjugated dienes. And reminder that a conjugated diene are two or more pi bonds with one single bond separating the pi bonds. So we call the pi system 1,4. The 4 carbons involved with the 2 pi bonds are the 1 through 4 carbons, and the 1 through 4 carbons have nothing to do with naming the molecule. The first reaction occurs when the pi bond between carbon 1 and 2, pi between C1 and C2, so those pi electrons are donated to the electrophile the partially positive hydrogen electrophile of HBr. And that's for this specific reaction. So that's the first step. Now, also in the first step, you always have to remember that when electrons are donated to an atom, if that atom already has a full valence shell, then you have to break whatever bond already exists to that atom. So hydrogen can only have one bond because to have a full outer shell, it has 2 electrons, and one bond is 2 electrons. So when you donate 2 electrons to hydrogen from the pi bond, you have to remove the electrons that were already bonded to that hydrogen. And so you have to show that the sigma electrons, or I could say the HBr sigma electrons move to a lone pair on bromine. So you have to show both of those arrows for the mechanism to be correct. And that's step 1. And then we can correlate the words pi electrons of C1 and C2 donated to H of HBr. So we have an arrow going from the pi electrons to the hydrogen. That describes the first step. And then we have that the HBr sigma electrons move to a lone pair on bromine. So now we have an arrow from the sigma electrons between H and Br, and it's moving the sigma electrons to bromine. And that's the first step. After this step, that's step 1. In step 2, what occurred in that case is that now C1 is now CH3. So it has a new C to H bond. So whether we make the 1,2 addition product or the 1,4 addition product, when we're adding HBr, the hydrogen bonds at carbon 1. Okay? And we produce 2 cations. we have two cations because of resonance. And those two cations are positive charge. So let's say cation 1 has the positive charge at C2 and second or remaining pi bond between or at C3, C4. Okay, so then cation 2 the positive charge is at C4 and the remaining pi bond is at C2, C3. So then if you go back and you look at your two cations, we have cation 1 with the positive charge at C1 is now has 3 hydrogens instead of 2. So we've increased the number of hydrogens at C1. We have a positive charge at C2 and a pi bond between carbons 3 and 4. Then we have a resonance arrow because this molecule is an allylic cation, and we can shift electrons to produce a resonance structure. When we move the pi electrons of the pi bond between 3 and 4 to between carbons 2 and 3, then the positive charge goes to carbon 4. So the pi that was between 3 and 4 moved to 2 and 3, so that 2 was no longer positive, and that gave us a positive charge at carbon 4. Okay, so having a positive charge at carbon 4 or carbon 2, some of the cations exist as the positive charge at carbon 2, and some of the cations exist as the positive charge at carbon 4. The electrophile, or the nucleophile for the second step bromide ion, will bond at carbon 2 for the cations with the positive charge on carbon 2, and it will bond at carbon 4 when the positive charge is at carbon 4. And this gives us our two products, the 1,2 addition product and the 1,4 addition product. And one thing to note is that these products are not equally stable because we have a monosubstituted diene and we have a disubstituted diene. And we know that disubstituted dienes are more stable. And that if for some reactions, the more stable product is going to be the major product. So we have to look at conditions for this reaction where we might have major and minor products because of one product being more stable than the other. So here's another example. Which one gets the proton, carbon 1 or carbon 4? We protonate the end that forms the more stable cation. So whichever position for the addition of hydrogen gives the most stable cation, then that will be the position that hydrogen adds to. So here they're numbering this, then the numbering 1 and 4 that they gave us is based on the name. 2-methyl, 1,3-butadiene. So there's a methyl group at carbon 2, and it's a diene with pi bonds at carbons 1 and 3. All right, so, but when we look at our 1,2 and our 1,4 addition, those numbers have nothing to do with the numbering for the naming. So we need to put in a different color, are we going to have for our diene addition, is carbon 4 going to actually be carbon 1 for the addition of hydrogen? Or is carbon 1 going to be where the carbon adds? Okay, and that's going to depend on where the positive charge is the most stable. So you have to look on both sides. If we have for our diene addition that carbon 2 is the most positive, we would get the cation, or most stable position for a positive, then we would get this cation. In blue, so that gives us a secondary allylic cation. And we said that a primary allylic is less stable than a tertiary allylic. So a tertiary allylic is the most stable, then secondary allylic is next, and then after less stable than secondary allylic is primary allylic. So if we draw the cation that comes from the numbering shown in red above, we would have CH3, C, positive charge, CH double bond, CH2. So this is a tertiary allylic cation. So I know what's going to serve as my carbon 1 for the addition of the proton. So numbering my double bonds my double bond carbons 1 through 4. In this case, the numbering of the double bonds 1 through 4 is the same as the numbering for naming, but it won't always be the case. But I'm choosing to say that my carbon 1 for the 1, 2, and 1, 4 addition is the one that gives me the tertiary allylic cation. And so this one, the secondary allylic cation, is less stable. And so not likely. So the two products are going to be made from the tertiary allylic cation, and the 1, 2 product would have addition at carbon 2, and the 1, 4 product would result from a shift of the pi bond so that we would have a tri-substituted pi bond. And even though that this is a less stable cation, it's a more stable double bond. And so for the final product, when bromine adds, the more stable position for the double bond is going to determine whether 1,2 or 1,4 gives us the more stable product. So we consider the more stable position for the positive charge when we are adding hydrogen, or the electrophile in the first step, and we consider the more stable position for the pi bond when we are deciding which is the more stable final product. And when we're deciding which is the more stable final product, we ignore the position of the positive charge and focus only on the pi. So these is the 1,2 cation, and that gives us the 1,2 addition product. Okay, and then we have the 1,4 cation and the 1,4 addition product. Okay, for the reaction of 1,3-butadiene with HBr, we're going to call the 1,2 product a kinetic product and the 1,4 product a thermodynamic product. And the literal meaning of kinetic in this case is fastest. So the 1,2 product forms the fastest because one hydrogen adds from the bromine the bromide, in that when this pi bond comes down and picks up this hydrogen, the proximity of the bromide is that it is closer to C2 physically closer to C2. And so bonding to C2 can occur more quickly. Okay, then what about the 1,4 product? The 1,4 product is the more stable final product because it is the more stable position for the double bond. It's disubstituted. So the thermodynamic product is going to be the more stable product. So the thermodynamic product should have the best delta G value. And it will have a lower energy, it's a lower energy product than the 1,2 product. So because they both have reactants that's equal in energy, when you draw the reaction graph, the 1,2 product, the final product will be higher energy, and the 1,4 product will be lower energy. And so the 1,4 product has the larger delta G, and that's why it's called the thermodynamic product. So the delta G difference is greater for thermodynamic product. Now I have to tell you that the 1,4 product will not always be the one thermodynamic product. Sometimes the 1,2 product will be both the kinetic and the thermodynamic product. So let's say 1,2 is always kinetic product because that has to do with proximity. And 1,2 is sometimes also thermodynamic product. And then 1,4 is never kinetic product. It's not possible. And is sometimes the thermodynamic product. Okay, so those are some notes that you need to keep track of. If the reaction is irreversible, then the kinetic product predominates. So if the reaction is irreversible, the kinetic product predominates. And the way that we make a reaction irreversible is to use very low temperature. So that would be one way that we could make it irreversible, to use a very low temperature. Because at a very low temperature, movement is slow. There's very little kinetic energy for movement. And so the carbon that bromine is closest to is the carbon that is going to be bonded to bromine, because the bromine is not going to be able to move over to the 4 position. So if we draw the cation, if we draw our 2 cations, after the addition of hydrogen, bromide is next to the position at carbon 2, and it would have to be able to travel to reach carbon 4. So bromide is physically closer to 2. Can I spell physically? PHY. And cannot move. Has a very low ability to move because the solution is so cold. Okay, so in cold conditions where there's a very low ability to move, note that the kinetic product predominates because that's where the bromide can bond based on what it's closest to after the hydrogen is added. So then in very warm conditions where the reaction can reverse, because it actually turns out that bromine is a very good leaving group and can readily be kicked off, where the reaction can be reversed because we have enough kinetic energy for substances to move around, then the predominating product is the more stable position for the pi bond, or the more substituted pi bond. So under warm conditions, predominant product is more stable or more substituted pi bond in final product, because that product will be more thermodynamically stable in terms of the value of delta G. So delta G has greater difference between reactant energy and product energy. Okay, so if you look at the graph, the kinetic product is reached more quickly, and so the transition state of the second step is smaller, so it happens faster. And then if you look at the overall value of delta G, we have the energy of the reactant, and then the energy of the kinetic product, and the energy of the thermodynamic product. And you can see here that the difference between the energy of the reactant and the energy of the kinetic product is greater. For the difference between the energy of the reactant and the energy of the thermodynamic product is greater. And that is the definition that we gave to more thermodynamic stability. More thermodynamic stability is greater difference between reactant energy and product energy. So the best delta G value is achieved when we have a thermodynamic product, and that's possible when we have warm conditions. Okay, so we can choose which product we want and control the reaction. In kinetic control, the reactions are irreversible, whether it adds to the carbon 2 or carbon, whether the pi bond ends up between carbons 3 and 4 or carbons 2 and 3, so that we have 1,2 addition or 1,4 addition. Both 1,2 and 1,4 would be irreversible in kinetic control. And the major product is the one that forms more rapidly, which is always the 1,2 product. In thermodynamic control, one or both reactions are reversible, and the major product is going to be the one that is the most stable and gives us the best difference in energy between reactant and product. So the most negative delta G value is going to prevail. Okay. In the reaction below, why is the 1,4 addition product the thermodynamic product? So the 1,4 addition product is the thermodynamic product because it is di-substituted. It has, each vinyl carbon has one alkyl group, so it's a di-substituted pi bond, whereas for the kinetic product, we have only one alkyl group, so this is mono-substituted, and this is di-substituted. And actually, when we do the 1,4 addition product, because we're going through a cation, we form a mix of the trans and the cis, or E and Z. And you have to remember that even in that, the E product should form more than the Z product because the E double bond is more stable than the Z double bond. Okay. Okay, so the transition states are not the reason, or secondary allylic cation to primary allylic cation is not the reason that the 1,2 product forms more rapidly. So the strength of the cation is not why 1,2 is kinetic. All right, so that's what this is about. And it has nothing to do with the transition states or the strength of the cation for determining what's the 1,2 product. All right, so that's their point here, secondary allylic cation, primary allylic cation. Technically, these two things don't actually exist. What actually exists is the resonance hybrid, right? So the resonance hybrid, you have to draw it below. And it's easy to forget that the resonance structures don't actually exist. What really exists is the resonance hybrid. So the resonance hybrid for the cation has the pi electron split from carbons 2 through 3, and the positive charge evenly distributed across those carbons. Okay, so all of those carbons have shared positive charge. All right. The correct reason for the 1,2 addition product is always the kinetic product, is the proximity effect that I was talking about earlier. And here they're using for their example, instead of HCl, they are using DCl. And remember that D is equal to a hydrogen within a mass number of 2, which means it has 1 proton and 1 neutron, whereas normal hydrogen, the most common isotope of hydrogen, has a mass number of 1 1 proton and 0 neutrons. Okay, so we call deuterium heavy hydrogen. All right. So just think of D as being equivalent to adding H. Okay. So once D adds, it has just broken its bond to chlorine. So this deuterium was bonded to this chloride atom. And when it bonded to the carbon, it broke, the bond between deuterium and chloride broke, but it's still close to deuterium. And it's physically closer to carbon 2 at that point than it is to carbon 4. And so it is, because of its proximity to carbon 2, that the 1,2 product is always formed faster and is always the kinetic product.